Hey guys, so let's talk about acceleration. First we'll talk about average and instantaneous acceleration, do an example, and then we can move into motion with constant acceleration. So average acceleration, let's just say that we have a particle that's moving along it moves from one position to another from time, let's say it's just some initial time to some final time. And during that time period, we also have a change in velocity. So we have some initial velocity and some final velocity. I'm going to go ahead and change these to knots. I just prefer not. Okay, so since we had a change in velocity, I'm going to have some change in, I'm going to have acceleration. And so we can define the average acceleration, and then we can write a little average is equal to the final velocity minus initial velocity, divided by the change in time, the final time minus the initial time. And that is the same as the change in time, the change in velocity over the change in time. And the units for this, since we have meters per second divided by time, is seconds. So it's meters per second per second, meters per second per second. And we normally just write that as meters per second squared. That's acceleration. So now we can talk about instantaneous acceleration. And the idea here is that we want to squeeze this delta t. We want to squeeze that down into some instant of time. And if we can do that, then we can tell what the acceleration is right at any given instant of time. And we can do that by taking the limit as t goes to 0. And that's going to be our definition for instantaneous acceleration. So our acceleration at any point in time in one dimension is going to be the limit as t goes to 0 of the change in velocity over time. And we know that the limit as I approach in a rate of change is going to be my derivative. So it's the derivative of the velocity with respect to time. Yeah. Okay, so let's look at an example. We're going to kind of walk through this a little bit. So suppose that we have the velocity of a car given by this equation. We want to find the change in velocity of the car in the time interval from t equals 1 second to 3 seconds. So A, we just want to find the delta V. So my change in velocity would be my final velocity minus my initial velocity. And now I'm just going to use my function. So that would be 60 plus 0.5 times 1 squared minus the entire quantity. You know what? Yeah, let's just do it. I was going to say we should break this up so that you can follow what I'm doing. But this is going to be the velocity at 1 second, and I'm subtracting the velocity. I'm sorry, this should have been the velocity at 3 seconds. The velocity at 1 second. So I get minus 60 plus 0. This should be 3. Plus 0.5 times 1 squared. So 3 squared, half of that is 4.5, so we get 64.5 minus 1 squared is 1, so minus 60.5. Subtracting those, I get a change in velocity of 4 meters per second. All right. So that's from 1 to 3 seconds. So find the average acceleration in the same time interval, the average acceleration. So my average acceleration is my change in velocity over time, or change in time. So my change in velocity was 4 meters per second divided by the change in time, 3 minus 1, which is 2 seconds. So I get that my average acceleration in this time period is 2 meters per second squared, or 2 meters per second per second. All right, C, find the instantaneous acceleration at time 1 second by taking delta t to be the first point. Okay, so what we're doing here we're going to change our delta t, and I know some of you were doing this in calculus last week. But basically what I want to know is, like, if I go back to my little picture, as I start shrinking this down, so if I want it from 1 second, I could say, okay, this is going to be, this is going to equal 1 second. And what I want is a delta t of 0.01. So we're going to move it closer and closer and closer until we get very, very close, and then we can estimate what that's going to be. I'm not going to go through all the steps, but I'll give you an idea of how it works. So A, B, we're on C. So the instantaneous acceleration at 1 second by taking delta t to be the first. Okay, I already know at 1 second, that's this quantity here. So that's my velocity at t equals 1 second. So what I want is I want my delta v to be my final velocity minus my initial velocity. And then we'll divide that by time. But first, let's just calculate it. So my final velocity we're going from 1 second to 1.1. So that my delta t is 0.1. So I would have 60 plus 0.5 times 1.1 squared minus the 60.5. And doing that, you get a change in velocity. Hold on 1 second. So we get our velocity at time 1.1 is going to be 60.605 minus 60.5, which gives me a change in velocity of 0.105 meters per second. So my acceleration is going to be that 0.105 divided by the change in time, which was 0.1. And that gives me an acceleration of 1.05 meters per second squared. Okay, we can go through the process again and we can get closer and closer, but it appears that as I take the limit, since this is going to be, this would change to 0.01, this is going to get a little bit smaller. So we're going to approach 1 is what it looks like. And now what we can do in part D is we can find the function for the acceleration, for the instantaneous acceleration. So D. So what we'll do is we'll find the acceleration by taking the derivative of the velocity function with respect to time. So we get the derivative of the function 60 plus 0.5 t squared. And we'll just use the power rule twice. So since I just have 60, basically what that is t to the 0. So I pull down the 0, this all goes away. So it's just this quantity. So I pull down the 2, and I get 2 times 0.5 times t, take away 1, that's it. So I get 2 times half, that's 1t. So my acceleration at any point in time is just be that time. That's convenient. So at 1 second, my acceleration in fact is 1 meter per second squared. All right. Let's see. I was going to talk about graphing, but I think we're just going to handle that in class. So let's talk a little bit about motion with constant acceleration. And then what we'll do in the next class is you'll apply it to free fall and motion on an inclined plane. So motion with constant acceleration. So we really don't want to talk about varying acceleration. We're just constant acceleration, good enough. So let's start with our definition of acceleration. So we know that the acceleration is the change in velocity, and I do that by taking my final velocity minus my initial velocity and dividing that by my change in time. However, whenever I have a particle that's in motion, we normally want to do an initial time of 0. So what we get is that our acceleration is going to be final velocity minus the initial velocity over, this would be, this part right here, again, would be TF minus T naught. But I'm going to set that equal to 0, so it's just over T. So however much time it takes if we start at 0. And rearranging this, if I multiply this over, I get A times T is equal to VF minus V naught, and then add this over to this side, and then I'm going to flip it all around. So I get VF is equal to, move this over, V naught plus the acceleration times time. So that's your first kinematic equation. The final velocity is equal to the initial velocity plus the acceleration times time. And this is nice because you should recognize this. This is in the form of y equals a plus bx. Or if we use the United States kind of stuff, it'd be b plus mx. So we can see that the m is my acceleration. So on a velocity versus time graph, the slope of the line equals the acceleration. Now, and it's nice and constant with constant acceleration. So now let's try to derive an equation for, so this was velocity as a function of time. And let's try to get one for the position as a function of time. So let's start with our definition of velocity. So velocity is going to be the change in position. So x final minus x naught over delta t. But we're going to do like we did before. So it's just over t. And if we think about, since our velocity is changing, then I also know that my average velocity, just put a little a over some time period, is going to be the average. So I can just add them. So my final velocity, or my initial velocity, plus my final velocity divided by 2. That would be my average velocity for constant acceleration. All right. So now we'll use the velocity equation that we just derived. So this equation 1 right here. Oh, where'd my pen go? There. Okay, we'll use this equation here. So I have that VF, I'm going to use this equation, equals V naught plus the acceleration times time, because I'm trying to get a position function that has the acceleration in it. So now we can substitute. So my average acceleration so we're going to use these three equations all together. And essentially what I want to do is I want to take this quantity here, my VF, and that's going to go in here. So let's kick that off to the side. So we have that our average velocity is going to be, if I pull out the 1/2, I get 1/2 times V naught plus the final velocity. So let's go ahead and substitute it in. So I get 1/2 of V naught plus V naught plus the acceleration times time. You know, I don't think I needed this. Anyway, so this is the average velocity. And then doing the arithmetic, we get that the velocity is going to be equal to, that would be 1/2 of 2 V naught plus acceleration times time, which is V naught plus 1/2 a t. So now we can use it. So this is my average velocity. You know what, I am going to use it. So now, you ready? Okay, so now we're going to take this one, and since we need to change velocity into position, and that's going to go in right here, and then we can do some stuff with it. So I have xf minus x naught divided by t is equal to v naught plus 1/2 at. All right, so now I multiply. What I want is I want to get this by itself, so I'm going to multiply everything through by t. So I get xf minus x naught is equal to v naught times t plus 1/2 a t times t is t squared, and then I move my x naught over. Xf equals x naught plus v naught t plus 1/2 a t squared. And that's your second kinematic equation. All right. I think that's good. There's one more equation, but I'm not going to go through the derivation. We're already at 15 minutes. So your third equation, we'll just write it over here. That's going to be your final velocity squared is equal to your initial velocity squared plus 2 times the acceleration times your change in position, xf minus x naught. Okay, that's your third kinematic equation. And these are all on your equation sheet right here. And you know what? I'll leave this as a derivation for you. So try to derive this. If you need to, you can look it up. But it'd be good practice because you'll be expected to do this. All right, that's constant acceleration. I guess the one thing we could talk about real quick is what the graphs look like. So when you have constant acceleration, let's think about the position, velocity, and time graphs. So we have position, velocity, and acceleration. So my acceleration will be a horizontal line. That's constant acceleration. And since it's constant, then I know that this is linear. So it's increasing like so. And my position graph, I'll get some kind of quadratic, which follows from my definition here. All right, and that's it. Okay. See you in class.